Hi everyone, good morning. Am I audible? Can someone confirm?
Yes, you are.
Yes.
Okay, thank you. So basically, today is the first recitation on how you guys can go about writing your first MLP or deep learning code rather. And we have divided it into two parts. The first part will be done by Abby, where she'll give you an overview of the theory behind it. And then in the second part, I'll basically take you guys through the code, the PyTorch code that is required. Just a couple of reminders. Today is the deadline for forming study groups. So please do that if you haven't already. After that, we'll be randomly pairing you guys. Quiz one is out. We have released it a day early. So make sure that you actually go through the lecture slides and the lecture recordings so that you do well in the quiz. Yeah, over to you, Abhi.
Okay. Can you see my screen right now?
Yeah.
Okay. So hello everyone. Welcome to the very first recitation. So in this recitation, we're going to show you how to write your first MLP code. So I'll be covering the first part, which is mainly theoretic. I'll briefly go over this whole model training process on a really high level. And the professor is going to dedicate 4 to 5 future lectures on this in much more detail. So in this recitation, just try your best to grasp like a overall idea. Okay. So first, the inspiration of the artificial neural network is our own brain, made up of connected neurons. A neuron is a node with many inputs and one output, and a neural network consists of many interconnected neurons. Information are transmitted from one neuron to another by electrical impulses and chemical signals. In order to enable a similar fashion of this transmission of information in the artificial neural network, we invented a computational model called the perceptrons. So it has 4 parts: the input values, the weights, the weighted sums, and finally the threshold or activation function. The single perceptron performs really simple arithmetic operations in the following steps. First, it multiplies all inputs with their corresponding weights, and then all the multiplied values are added together to get the weighted sum. And finally, we put the weighted sum through an activation function or threshold function. As we have already shown in class, a perceptron which performs an affine combination of the input values with a threshold activation function is a linear binary classifier. So what if we want to be able to distinguish the data into more classes, or what if the data is not linearly separable? What we can do is to introduce more perceptrons or more layers of perceptrons called multi-layer perceptron or MLP. So in an MLP, we usually have these one input layer, several hidden layers, and a final output layer. Yeah, so above is just a quick recap of the basic structure of an MLP, which you should be quite familiar with right now. However, in order to correctly classify things, our MLP must be learned. So before we get into the learning process, the first thing we should make clear right now is what actually needs to be learned. So take a minute and think about this, because once we enter into the training phase, the layer number of the MLP is fixed. The number of perceptrons contained in each layer is also fixed. And each node here would be performing a fixed set of operations. So once we go into the learning or training phase, the only thing that we can change now is the weights. So what we are actually learning is the parameters or the weights of our MLP here. Okay, When we're trying to do a classification task, we're actually trying to map each data onto its corresponding class. So this is actually just a function, but our problem is we don't really know what this function looks like or what the exact formula of this function is. What we only have is these sample data points located on this function, represented by these red dots here. And our goal is to give an estimate of the classification function with these given samples. Okay, so since we're trying to estimate a function that we don't really know what the exact formula is, we need an alternative measurement that tells us how good our current estimate is. So note that the only thing we can take advantage of is these sample data points. So these measurements would be telling us how much off is the network output with respect to the desired output. And we would often call this the loss function. So here, as you can see, the loss function is a function with respect to the weights. And for each sample, F, which is the MLP, and Xi is the value of the sample data points, and W would be representing the current weights of our MLP here. So F of XIW would be our current network output. So this basically reflects how our current model is classifying this particular sample. And then D here is the desired output or the actual class of our sample data points. And div is a divergence function. So a divergence function is basically a function that measures how far off these two values are. It generally goes to 0 when the two values are equal. And you'll see a couple examples of these divergence function in future lectures. And finally, we'll just take an average over all the divergence of the sample data points. Okay, and now we have a measurement telling us how good our estimate is. We can specify our goal more specifically. So our goal would be to find a set of parameters that actually minimizes this loss. So this is what it looks like in a mathematical form. And now the final question is, how do we actually find the set of weights that actually minimizes this loss? And the answer is to use gradient descent. So gradient descent is basically an iterative optimization algorithm for finding a local minimum. And in our case, we're trying to find the set of weights, which is like the X value here, to minimize this loss function. Gradient descent basically works by taking repeated steps in the opposite direction of the gradient of the function at the current point. It's okay if you're not that familiar with this concept. We will be going into much more detail in future lectures. So as I mentioned before, gradient descent requires us to calculate all the gradients of the error function with respect to each weight. And this could be quite problematic if we have many parameters, and this would be especially inefficient for the weights to the frontier part of the layers. So a solution that we have is called the back propagation. So the back propagation works by computing the gradients of the loss function with respect to each weight, starting from this very last layer here. And it goes backwards one layer at a time to avoid any redundant calculations of intermediate values in this chain rule. If you're familiar with dynamic programming, this is actually an example of that. Okay, so this is basically the whole framework of the training process. I'm going to walk you through these process again with these graphs. So recall here that for a single perceptron, A forward pass includes calculating a weighted sum and taking it through an activation function. So our training process would start with the forward pass, which is basically trying to calculate the f of xw in the loss function that we had before. So we'll do the forward pass layer by layer. Here is all the output value of the first layer. And then the second and the third. And finally, we have these network output here. And then we'll calculate the error or loss function with respect to the desired value here. And after we have the loss, we'll enter into the back propagation phase. So notice here, we will first try to calculate the error over DO. So this is the gradient of the loss with respect to the output value here, which is not really needed in the gradient descent, but it would be really useful when we're trying to calculate the gradients of the weights here. So this is an example of calculating intermediate values. So when we go one step backwards, as you can see here, the gradients of the loss with respect to the weights here by the chain rule is actually d error over do times do over dw. And since we already have the error over do, the only thing that we need to calculate now is do over dw. And similarly, we would go backward like this. And here, again, the only thing we need to calculate is dy over, yeah, I think it should be dw here, I'm sorry. So we'll just go backwards similarly until all the gradients of the loss with respect to the weights are calculated. And our final step is just to update the weights. So here, eta is a hyperparameter called the learning rate. It basically represents how fast you want the parameters to be updated. And this is the gradient that we just calculated. Okay, so this is the whole training process, and we'll go into the coding part.
Yeah, thanks, Happy. I hope you guys got everything that she explained. If you guys have any questions, I'll give you guys 1 minute to ask them.
Okay.
I have one question. So for gradient descent, like, do we calculate the gradients individually for every perceptron, or we calculate it together for one layer?
So for gradient descent, what we want is the gradients of the loss with respect to each weight in the MLP. So we definitely want each gradient of the loss with respect to each weights, but we'll do this layer by layer just to reduce any redundant computation. So.
Okay. Thank you.
Yeah.
Abby, I think there's a question in the chat.
Okay. Are we updating the biases as well? Yes. So bias is just a special kind of weights or parameters. So we are updating these, and the loss movement in back propagation. Okay, so back propagation is a method that we're using to compute the gradients of the loss with respect to each weight efficiently. So we're doing this starting from the very last layer backwards, so that at each layer or each iteration, we only have to calculate the gradient of the output value with respect to the weights. And this output value could be the output value of the perceptrons to its, I guess, Arun, can I share my screen real quick? Yeah, so here, as you can see, we will start from the very last layer, and we'll first calculate the gradient of the loss with respect to this output value here, DRO over DO. And we don't really need the gradient of the loss with respect to the output value when we are doing the gradient descent, because we only need the gradients of these weights in the intermediate, like in between these layers. However, we want to calculate this because when we go on to the next step here, the gradient of the loss with respect to the weights here by the chain rule is equal to d arrow over do times do over dw. So do over dw is the gradient of, or the derivative of these output value with respect to the weights here. So by back propagation allows us to only calculate this latter part of the gradient when we go into this phase. And similarly, when we goes on, when we calculate these the gradients of the loss with respect to this output of the hidden layer here, we only have to calculate dO over dy, since this front part is already calculated. And yeah, this is just another similar example when we are calculating the weights at this layer by the chain rule is equal to like DRO over DO and times DO over dy, which is the output of this hidden layer, and dy over dw. So these two values are already calculated, and the only value we need to calculate now is the derivative of these hidden outputs with respect to the weights at this layer right now. Yeah. Is this clear now? The slides are already posted on the website, and yeah, so in backprop, we're going layer by layer backwards. So what do you mean by jump here? Because as you can see here, the layers are connected. So the definition of layer is like, so as you can see by these arrows here, we don't have an arrow from, for example, like layer 1 to layer 3. Since the fashion that they are connected makes the back propagation possible, because for example, like the weights in this layer here, they are only contributing to the outputs of the hidden value here, a hidden layer here. So you don't have those jumps in back propagation. And another question is, are we doing gradient, as we are doing gradient descent, do we get the current weights at the end of the backward pass, or are we doing several forward and backward iterations? Yeah, so this whole, like this forward pass and backward pass example here is just one iteration. So we'll do a couple iterations of these training paths until the error or the accuracy kind of plateaus. We haven't get into the evaluation part yet, but just know that during the actual training phase, we're actually doing several passes of this or several iterations of these. Okay. I think that's all the question I have.
Okay. I'll take over the. I hope you guys can see my screen.
Yes.
Okay, thank you. So yeah, as you will see in the coming weeks as well, we in IDEA love memes. This is just some of the memes that I've collected for this recitation specifically. Yeah, and so I'll be going through the topics. What I'll be doing is I'll be stopping at specific intervals to ask if you guys have any questions. In the middle, if you have any questions, just raise your hand and I'll ask and I'll stop if possible, or else you can ask me in the chat as well. So this is going to be the summary for today. The first topic will be tensors, which I am guessing all of you guys are now familiar with after doing homework 0. The next will be CPU and GPU operations. And the last bit will be components of training a model, which is the most important part of this recitation. First of all, can someone tell me the difference between tensors and Numpy arrays?
Tensors store like other information as well, right? Like they can store gradient information and things like that.
Those are just numbers, right? When they're storing the gradient information, it's just numbers. So can arrays. Like, what's the actual difference between a tensor and an array?
Tensors also store the computation graph, right?
Okay. Any other?
Numpy arrays, they are just like two-dimensional or maybe multi-dimensional vectors.
Okay. Let me go about this another way. Are Numpy arrays immutable? Anyone?
Tensors are immutable, numpy are mutable.
Right. So that's one of the major differences. So even if you basically have a tensor giving 2 plus 3, every time it will have those computations again, and that value will be basically calculated or computed. And tensors are immutable, they cannot be changed in one execution cycle. And apart from that, tensors are specifically designed to be optimized via GPUs. So they do have significant, so whenever you're training a model for using GPUs, you will switch to tensors. Yeah. Okay, so I am guessing all of you guys are aware of this. PyTorch tensors are very similar to Numpy arrays, and you can switch from one to the other pretty easily. So over here, I've just given an example of that, where there is a tensor A and an array B, and we are just comparing whether it's the same or not. And as you can see, it's the same. Another example that we've given here is actually doing the matrix multiplication and checking if the results are same or not. And as you can see, they are, which is as expected. Next, we'll go over CPU and GPU operations. So the main difference with PyTorch tensors is that you can perform operations on the GPU as opposed to the CPU. And trust me, that helps a lot. You will reduce your training time by 10 folds at least. And which is why whenever we are training models for part 2, we'll only operate with tensors using PyTorch. In the below example, the screenshot, I've basically given time comparison for Numpy and tensor operations. And as you can see, the GPU time taken is significantly less. One thing to note is that to do GPU tensor operations, you must first move the tensor from the CPU to the GPU. By default, whenever you're reading in a file, whenever you're creating an array, by default, it's on the CPU. So you need to move it to the GPU to utilize that GPU. And the second point, this is the most important one, that operations that require all components to be on the same device, otherwise they will fail. Many of the times this will happen with you that you forgot to move one of the tensors to the GPU, and then these operations fail with extremely weird error messages. So this is the reason you need to first verify whether all of your tensors are on the same device. It can either be the CPU or GPU, depending on what you're doing. If you're training a model, they would ideally be on a GPU. If you're just creating a result file or a submission file for Kaggle, then it will be on the CPU. Yep. This is an example of this. By the way, the link to all of this code is at the end of the slides, and this slide deck is already uploaded on the deep learning website. So over here, you can see that the A tensor was actually moved to the CUDA device, which is the GPU, but B was not. And whenever you're trying to do any operation between the A that is on the GPU and B, it will fail. Okay, things to keep in mind here, that a GPU operations runtime comes in two parts. The first one is the time taken to move a tensor to GPU, and then the time taken for an operation. In most of the cases, the second part is going to be extremely fast, which is going to make you want to work on a GPU. But for small tasks, the reason we don't suggest it is that sometimes the point one, which is time taken to move a tensor to the GPU, can be extremely high, and it kind of defeats the purpose of using the GPU in the first place. But all model training should be done on GPU. If you start training models on CPU, this is what you will look like by the time your first model is trained. Okay. Important thing to note is that if you're using Collab or AWS or whatever you're using, GCP, Azure, the GPU memory is quite limited, and it's extremely expensive as well, as you guys might have noticed by now. So you'll frequently run into this error that CUDA is out of memory, and it tried to allocate certain memory chunks, but was not available. That happens quite often. So you need to ensure two things. That first of all, there are no dangling unused tensors left on GPU. And whenever, I would suggest whenever you're trying to do a part two code, take a small sample of the data, like the first batch, and run your entire code on CPU. So try to train the model using just one batch. So like 50 to 100 instances on the CPU first. Once you've ensured that your entire code works, then run it on GPU. And please don't read the data into one tensor and then use it as another tensor in the data loader, because that will just result in a double memory utilization, which is not ideal. And second thing that you can do when you get this error that CUDA is out of memory is that you reduce the batch size. So every time it tries to train an every operation, it will have less data to deal with, and keep on frequently doing torch CUDA empty cache after deleting any tensors or any dangling tensors that you find. Okay, I'll wait for a minute here if you guys have any doubts up until this point. Okay, there is something on the chat.
There's a question in the chat, I think.
Yeah, I'm looking at those questions right now. I found A to CUDA is quite slow for my EC2 instance. Is this normal? Yes, just like I explained here, it consists of like two steps. The first one is time taken to move a tensor to GPU, and this is sometimes quite high, but it shouldn't be extremely high. Does that answer your question, Alan? Okay. Does the GPU have a garbage collector? You always have to clean it up by yourself. It does, but it does not work as efficiently. And in fact, even after you do this, sometimes it won't work and you will just have to end up restarting the entire instance and starting from scratch, which is why I suggest that first run your code for a very small block on this very small batch on your CPU, test if the entire code works, and only then move to the GPU and make sure that you're not utilizing unnecessary memory anywhere. Sorry, Prabsimran, what is the point that you wanted me to repeat?
So you were mentioning something related to the tensors that we might be using like double memory or something by doing.
Okay. So that is basically, let's say if we give you a data set to work with and you read it into a variable A, okay, and then when you are obviously aware of the data set and data loader classes, right, by now from homework 0. So let's say in the data set class, if you are accessing it through A, then it creates a temporary double memory utilization. Which is why we suggest that you directly read the file in your dataset class itself.
Oh, okay. Thank you.
Yeah. Can we enable some sort of GPU mode in PyTorch? Do you manually need to run to Collab for each and every small element? How efficient is it to code? The toCUDA or CUDA function is I would say it's moderately efficient, so it does not result in a lot of delays. There is a device that you can specify, but you will have, like, there is a device argument that you can specify that if CUDA is available, then CUDA is the device, but you will have to move all the tensors onto the device. And you are never going to deal with 50 tensors that you have to move. In most cases, it will be 4 to 5. Does that help? Person? Okay. Okay. Set device. Yeah, exactly. Just like Chandra said. Is there any literature you can point us to regarding the time trade-off between access to CPU versus GPU? I don't know of any such literature because every time you're using a particular data set, it's going to change depending on that. But in any case, like whatever the trade-off might be, if you're training a model, you do it on the GPU. Does that help? Yeah, let's see. Okay. Okay, so in order to avoid memory problem, the GPU better delete them from GPU after compilation. The deletion operation is not costly. Every time you move the array to GPU, you need not delete it that time, because one copy of the array is on the CPU, the other is on the GPU. So it's not exactly utilizing a lot of GPU memory. It is just utilizing what it needs. So you don't need to do that. If tensor is immutable, how does grade update, how does weight update work? We'll go through that soon. So in the next couple of slides, we'll go through that. Could you give an example of directly loading the data instead of accessing from the output of the data loader? Not sure. Okay, let me find if I have any such example. Can you guys see my Chrome screen?
Yes.
Yeah. So Audrey, just to answer your question, right? So as you can see in the dataset class that I've defined over here, I have given the load functions directly in the dataset class rather than loading them earlier and then giving it to the dataset. Is that clear now? Okay. Then we have Jeffrey. Is dataset the one that will create duplicates in memory or data loader or both? So neither dataset nor data loader will create duplicates. It is you who will create duplicates by reading it first into a separate variable and then using that variable in the dataset. Okay. Next is from Neil. Is this why you delete gradient tape after computing gradients in TensorFlow? I am not that experienced with TensorFlow, so I don't exactly know what gradient tape is, but assuming that you are referring to the same thing, no, that is not why we delete gradients. We delete gradients so that they are not carried forward to the next batch. Does that help? Okay, perfect. Any other questions, guys? Otherwise, I'll move on. Yeah, 0 grad, exactly percent. Okay, next, we are going to go through. Okay, there is. Okay, here we go. Yeah, next we'll go through a very important topic, that is debugging. Because although what you're learning is deep learning, you will spend roughly 80 to 90% of your time just debugging your code. So that's why I'm just going to go through some slides on debugging as to what you can do and exactly what options do you have if you are stuck in a pickle. Okay, I have a meme for this as well. Oh yeah. So this is what happens. The first time you're going to lose your mind, ignore TensorFlow, insert PyTorch. But the first time you're going to lose your mind debugging the PyTorch code. But once you do it for a few times, you're going to exactly understand, depending on the error, where you messed up. Okay. So these are some of the things that we suggest that you do when your code breaks. So look at each error message and expand the list of commands or the trace that lead to the error. This is what we've suggested to a lot of you when you had problems in the Autolab submissions as well, that go through the trace, understand what is happening in the trace, because that is one of the most important things. And a lot of the trace will not be your code, they'll be packages. So if you're using PyTorch, it'll be some internal error in a PyTorch function or something like that. But you need to understand what line of your code is exactly leading to that error and if you're using the functions correctly or not. A great way to do that is to read the documentation, which I know every one of us hates, but is extremely important. Then if you cannot still fix the issue, you should just Google your problem. People dedicate half of their days to just solving people's problems on Stack Overflow and GitHub issues. So you can do that. And if you have no clue what they're doing, just go and study the documentation because that's how they learn what they know. And you might think this is a waste of time. It's not. And it's a very good habit to actually read the documentations and have it open when you're coding. Especially when you're new to PyTorch, I would suggest that you have the torch.nn, which is the neural net. Yeah, the torch.nn documentation open so that you can understand how to use each of the functions. And this last step is existing just because you are in a class setting where you can actually ask the TAs on Piazza, submit a problem to Piazza, or you can come to our office hours and clarify. We'll be able to solve most of the issues since 6 months, a semester or 2 semesters back, we were in your exact same shoes. And we know we have faced these errors, so we know what the exact issues are. For extremely common issues that we know that everyone faces, we'll actually ask you to go online and look for this error. This is not because we are lazy, trust us. This is to get you into the habit of actually debugging and solving the issues that crop up in your code. Okay, next, okay, this error right here is the worst error that you can get, CUDA error, because you don't exactly know what is happening. Okay, which is, again, I'll repeat myself that this is again why I asked you guys to go through a small batch and run it on CPU first, because CPU operates in a way that you can actually understand. It's not parallel, right? It's sequential, so you can understand where exactly the error happened. But when you're using a GPU, more than half of the almost all the operations are run in parallel. That's why it becomes extremely difficult to pinpoint the exact error. But it could be most likely one of these three, where you did an operation between the CPU and GPU tensors. So you've not moved all of your tensors to a particular device. This is when that is when this can happen. Or you did GPU operations between tensors of unexpected shape, which is likely the most common cause. And this is why, again, run your code on CPU first, because all of these shape issues you'll be able to understand pretty quickly on the CPU. And your data types were wrong in some weird way. This happens very infrequently, but it does happen that sometimes it gives a long data type and it expects a float or something like that. You just need to typecast. But yeah, it could be because this is like the last option, the last possible error. And yes, the lines that trace back may not show the actual source of error because GPU operations are parallelized. You should try running the entire thing again after setting launch blocking to 1. This will essentially run everything in sequence, and it'll be easier to pinpoint the error. And remember to turn this back on after you are done debugging, because otherwise your model is going to train extremely slowly. Yep, some notes on working with Collab. Collab is great, it's free. Although a quick update, Collab is no longer great because up until last semester, it used to give us Tesla V100 GPUs and P series GPUs for just the Collab Pro, that is the $999 per month. But now it gives K80s, which are not that useful. So maybe it's the right time to switch to AWS. I don't know. Now Collab has another tier of subscription, that is Collab Pro Plus, that is $50 a month. That is extremely high. But yes, apart from that, Collab is generally great because you don't need to do a lot of setup and it does not involve a lot of headache. Just go to collab.google.com and start coding. And yeah, so when you get a device side assert on Collab, you probably have to restart the runtime instance. And if NVIDIA SMI, I think that command was in one of the recitations, shows clogged GPU memory, you have to restart the runtime instance. And yeah, take note that Collab is free, but you're trading your own time for it, especially the free version. The free version is almost a huge headache now. So I would suggest taking either the Collab Pro or sticking to AWS. Yeah. Before I start, yeah, I'll stop for 1 more minute for any questions that you guys might have regarding debugging. Or if you faced some common issues during homework 0 and did not know how to go about it, then yeah, I can probably help you out there too. Is Collab Premium useful? I believe you're referring to Collab Pro, which is $10 per month. It used to be useful. Like, you'll definitely get better GPUs than the ones that you get for Collab free, the free version of Collab. But these days, there is a very, very small possibility that you will get Tesla V100s, which is actually the best among the GPUs you can get, and that reduces your training time by a lot. But yeah, overall, rather than using Collab free, I would still suggest Collab Pro because it gives you better GPUs. Is it a good idea to debug on CPU and then transfer everything to GPU after everything is fine? Yes, Alan, that's exactly what I've been saying. One of the recitations, it was mentioned that use Kaggle for data download. Is this like wget on the server directly? Actually, there is a library, the Kaggle library that you can have on Python, and then it's just one command that you need to run. And if you go to the data part of any competition, right, Kaggle has that command ready for you. So you can just use that. Yeah. Can we use our $150 course vouchers on Collab Pro or need? Sadly, we can only give you guys AWS vouchers. We cannot give you Collab vouchers because Collab runs through Google Payments and we don't get vouchers for those. Yeah, your vouchers are going to be AWS specific. Okay, just keep that in mind. Any other questions, guys? Okay, I'll proceed then. This is the most important part of the recitation. Obviously, it's the components of training a model. Over here on the right top, you can see that we've divided into 5 parts. The first and foremost is the data. The second is the model that you're going to use, the loss function, back propagation, and finally the optimizer. Yeah. So training a model can be defined in the following 5 steps. We get data, that is the pair of questions and answers. For any pair, we run X through the model and get the model's answer by cap or by bar. Then a teacher gives the model a grade depending on how wrong Y bar is compared to the true answer Y. And then based on the grade, we figure out whose fault the error is. And then we fix the fault so the model can do better next time. So it's just like there are a lot of evaluation components in IDL. You get overall score, and then you see, okay, where did I mess up? Did I mess up in the quiz? Was it homeworks? Was it the project? In project also, there are a lot of components. So was it the peer grading? Was a video not good? So that's essentially how the model functions as well. We'll go through the first part now, which is data. So data is generally a long list of XY pairs. I think list would be wrong, an array of XY pairs, where you want the model to see X and then predict Y. So PyTorch has 2 classes that you will need to deal with the data set and data loader. Thankfully, because of the pre-semester homeworks and recitations this time, you guys are already aware of both of these, data set and data loader. Dataset class is used to pre-process data and load single pairs. So in the dataset class, you'll have functions like the length function, the getItem function, the collate function, and all of that. And data loader class just uses your dataset class to get single pairs and group them into batches. So the batch size and everything that you're going to define is going to be in the data loader function. Right. So this is an example. So any dataset class needs to have these 3 functions for sure. That is the initialization function, the length function, and the getItem function. Yeah. So you use the initialization to load in the data into the class. So over here, we've used some previous variables that were already defined, X and Y. But this is exactly where I told you guys, rather than giving it X and Y, directly load the array over here using Numpy. Then the length is just the length of the results, or it depends, depending on the task that you have. If you're trying to transcribe audio to text, then it would be something different, which you guys will go through as you go through the part 2s of the homework. The last is the getItem function, where if given an index to the dataset class, it will basically get the X and Y pair corresponding to that index. Yeah, and yeah, one thing you need to note over here is that the get item function will be called a lot of times. So make sure that you do the least amount of work that is required over here. So let's say if you have to pad the function, or if you if you have to pad the array or do anything like that, do it in the initialization function itself, because the initialization function will only be called once, as opposed to the get item function, which should be called a lot of times. So minimum processing over here. Yeah, then comes the data loader. So this is an important argument as well, where you specify the number of workers or the number of cores. So if you have CUDA, then it's it, and you can't just write if CUDA. CUDA has to basically be true or false depending on if you actually have CUDA is available or not. So else 0, and over here this is the dataset class. These are all the arguments for the data loader class. And here you will go through, you will just give these arguments to a data loader class. Now we'll go through each of these arguments in detail. Shuffle equal to true. Shuffle will essentially, as the name suggests, shuffle the X and Y batches. This you have to do when you are training a model for the trained data set, but please make sure that you don't do it for the validation or the test set, because then your results won't match to what the actual results are, and then you'll end up getting low scores, and you'll scratch your head trying to figure out if my training accuracy is so good, why is my validation and testing so bad. Batch size, this is the concept of mini batches. I don't believe is covered in the lecture yet, but once that is covered, you'll understand what the batch size is. So you essentially group 256 X pairs and 256 Y pairs together and run an entire model computation on it first. That is what the batch size is. Number of workers is just what we've defined here. If you have a GPU, you can use many. If not, you can't. And pin memory equal to true. This is just something that makes data loading faster at the expense of more RAM usage. And obviously, this is these are the arguments when you have CUDA available. If you don't, then your batch size will also become smaller. Okay, now we have our data setup. Now we're going to worry about the model. So we'll divide into two parts: how to generate the model you'll use and how to run the data through data sample through the model. But I'll stop for another minute here, since this is a lot of information to process. So if you guys have any doubts over here, please feel free to go ahead and ask.
I have a question. I remember in the homework 0, like in the data set question, instead of like besides the init get length and the get item, there's another function like do something like the torch the batch. What's
The
that?
collate function, right?
Yeah, I think that's the one you're referring to. Like, what's that?
So the collate function, what it essentially does is when it runs the get item function, it will just group them into batches, into the batch size that you've defined here. One thing is that PyTorch has some inbuilt collate functions, which are way faster. So unless you really are doing something custom and needed, just use the default functions. Don't create your own function, because that will slow down the code.
So we don't necessarily have to implement that function.
For some homeworks, you might have to, because what you're doing is something unique. You're not just directly, you will not be able to just directly use what PyTorch has for you. In those cases, you'll have to write the collate function, but try to avoid it as much as possible.
Okay, thank you.
Yeah. Okay. Sorry, did I answer if tensor is immutable? I am just parking that question for now because it's going to come up later. So I'll answer it that time. In outside world, do we shuffle validation sets? No, we ideally don't, because while we're training the model, we need to get the validation accuracy as well, right? And that will completely mess up if we shuffle the validation sets and it does not actually match with the answers that we have. Suppose we are using a PC, what is the maximum number of workers we can specify? It depends if your PC has a GPU or not. And in most of the cases, PyTorch, let's say if you even define the number of workers as 8, right? PyTorch has this cool new update where it will basically tell you that depending on your system configuration, we suggest that your number of workers should be so and so. Why will shuffling the validation set affect validation accuracy? Because you won't be able to match it with what you have as the ground truth or the real truth, which is why. Doesn't shuffle on data loader shuffle both X and Y? So we shouldn't get low validation. It shuffles both X and Y. Okay, so see, X and Y are part of both the training as well as the validation and the testing data set. It's not like X is the train and Y is the validation. X and Y, part of X and Y is part of the training data set, and the remaining part of X and Y is part of the validation data set. Data loader data, which so what does data refer to here? That's just what we've imported. So we've imported it from Torch. So that's the class and it has the function data loader. Why shuffle for training data set? Any benefits? Yes, shuffling for the training data set actually helps. Okay, wait, I'm missing the yeah. Shuffling for the training data set actually helps a model learn better since it generalizes well, and it ensures you'll go through this theory. I don't know if I should say it, but well, you're looking for an optimum point in the curve, right? And if you cross it, then you need to come back, and as soon as you keep reaching near it, you need to take smaller and smaller steps. So shuffling helps you find that optimum point, because if you go in a methodical way, it is possible that you might actually miss it. Does pin memory parameter pin the full data set in the RAM or some batches? It will do it for the mini batches as soon as the data loader starts loading. Get item should contain as few. What sort of operations could we use? Yeah, you can use you can basically use reshape, float, convert, do some typecasting, convert it to long, and all of those things. Or if it's possible, you can do it in the initialization as well. Just keep the get item as few as you can. Obviously, you can't avoid certain operations, and those you'll need to keep in the get item function. Can you specify how much of the data you want to print to memory? Not really. Why the batch size for GPU is larger than the one in CPU? Because GPU is working in parallel, and it has and it can compute more operations than the CPU. Relating to your previous point of not creating local copies for the data loader, is that no, local copies was for the data set, not for the data loader. I'm sorry if I use that word. I think shuffle avoids biases on this. Exactly. It will help you generalize well. What exactly isn't matching? Okay. For the validation set, right? What you're doing is the model that you've already trained, you will run the X or the questions that you have through the model that you've trained in the training phase for the validation questions. And you'll get certain answers from the model. Then you'll try to match those answers with what we already have, which are the true answers. And if you shuffle it, the order is not going to match. So that's the thing that won't match. If you've already partitioned the data into train, val, and test set and shuffling, okay, my battery is low. I'll be back in a minute, guys. Sorry.
Yeah, I think Errol may have some issues. Maybe we'll just have to wait him for a minute. But just for shuffling, basically when you're training the data and without shuffling, you would have like a fixed pattern. So for example, you have X, Y, and Z, and you always input them into your model in this fixed pattern. Without shuffling them, you could have like the value, like this data point Y might be biased by X and Z. So the model would learn this pattern of X, Y, Z instead of the data point Y individually. So by shuffling them, we avoid this kind of behavior. Yeah, I was just explaining shuffling right now.
Thanks, Abhi. Okay, where am I? If you've already partitioned into that shuffling file independently, should it affect the scores, right? Yeah, it does. I think I explained. If you guys have any further doubts, please ask on Piazza. We are running out of time. Usually the training speed increases rapidly when we move from 1 to 2 workers, but I'll change that much more for more than 2. Why is that? No, I have never observed this, to be honest. Like maybe the increase is not as much because it spends some time in actually parallelizing the tasks. So dividing it into 4 workers, but overall it still increases the speed of training. Okay, by shuffling data, you ensure that each data point has independent effect, right? Sorry. So XY pairs are being broken during shuffling. No, they're not. They're not being broken during shuffling, but when you're comparing it to the true Y, so you're going to shuffle the data, right? And then the model gives you an output according to that shuffle. And when you actually compare it with the Y that you have, it will give you wrong results. K-fold cross-validation, I think some implementations do shuffle both the training, but we can do only if you're careful enough to design that we can easily grab the shuffle. Yep. If I pass both train and validation set as a parameter and we see a pattern of overfitting, will PyTorch detect that and return a non-overfitting model? Not really. Dealing with overfitting is what you will do by adding some batch normalization, by adding some dropout layers. So that's something that you will do. Okay, I think we are up to date with the questions. I'll move on. Right. So yeah, now that we have our data set up, next we worry about the model that we're going to use. This section will be in 2 parts. The first one, in class, you guys have already seen the MLP or the multi-layer perceptron. A bunch of these single perceptrons put together are called linear layers or fully connected layers. And a linear layer is a connection between the 2 layers as shown on the right. The layers themselves is an input vector being run through the network. So this essentially has 3 layers, 1, 2, and 3. So it's essentially the collection of weights. A key thing in neural networks is modularity. The network on the right can be broken down into 3 essentially same components. And this is what Abby was trying to explain when she went through back propagation, that you'll do it for the entire layer at one time since they are modular. So when coding a network, break down the structure into small parts and take it step by step, rather than trying to code this entire thing at once. Just go step by step. First declare this layer, then this layer, and then finally the output layer. So next we'll go into coding a model in PyTorch. So generally the networks in PyTorch are based off of the nn.module class. Here you will find the linear layers, the CNNs, the RNNs, everything. And similar to the dataset class, PyTorch wants you to implement the init and forward methods. So initialization is something that you'll have to do. And another is the forward method. PyTorch automatically takes care of the backward method through its computation graph. So initialization is where you actually define the model itself. And the forward method is where you pass your input X through that model or run it. Okay. So yeah. So if you see the documentation, it's pretty clear. The nn.linear class represents a linear layer or fully connected layer, and sorry, I meant the MLP is a model class, and it has a forward method, and the arguments that it takes are the in features. So incoming, how many features are actually coming into it, how many features are actually going out from it. So that is the in feature and out features. And if you need to specify the bias, if it is set to false, then it will not learn a bias, otherwise it will. And always you need to worry about the shapes. So whenever you're defining a model, please be sure to first check your input shape. And then after every layer in the model, I would suggest that when you're running it for the first time through one batch or on a smaller version of the data, print out the shapes. Print out the shapes and just check if they are matching with the next layer or not. Yeah, so this is an example of the model that we have. This is a very basic example. You can optimize. You don't need to write this again and again. There is another way that we'll show you during some of the homework boot camps. So the three layers defined in the init, the initialization defines the model. So this model has three layers. The first one has 3 inputs, 4 outputs, 4 inputs, 4 outputs, and then 4 inputs and just 1 output. Okay, and in the forward function, what you'll do is the X, that the data that you have, you'll take it through the first layer, the output of that you'll take it through the second layer, and the output of that you'll take it through the third layer to finally give you the output. So you need to run it sequentially one by one. And each of these layers has trainable parameters, that is the weight and bias. And by calling the parameters on your model that you've defined here, the R model class, you'll see the weight and bias of each layer. And you can also print the model to see all the components. So this is just if you messed up, like you wrote layer 2 here and layer 1 here. So just to verify before you actually start training, it's a good idea to print your entire model and see that everything is as per what you want. But yeah, one thing that you need to understand over here is that this is printed in the order defined in the initialization class and not in the forward. Okay, so as I was saying, it can get irritating writing this again and again. So for that, we have the nn.sequential module, where instead of writing this entire piece of code, you can just write this. This should be X, not out. So what you're doing is you're defining layers as a list. And if you guys are not aware, please search what args and KW args are on Python. That will help you understand how the list is actually unraveled. So if you pass the entire list of layers to the sequential module, it will actually create the layers on its own, and then you just need to specify self.layers X. Again, this should be X. Yeah, and this is what it essentially does. It is going to just take these layers, unravel it. This is, both of these operations are the same. And we've covered only the linear class as of now, and that's what you've been taught as well. But again, there are many more classes in PyTorch, and you should always have the NN documentation open, because that will have everything that you need for all the classes that you will require as far as the frameworks go. So linear, CNNs, RNNs are all in this documentation, and it is very thorough. So they explain every bit of the arguments, what is exactly happening inside, what are the computations happening inside, and what is the output that you'll get. And for optimizers, you can refer to this documentation. We'll go through optimizers now. Last. Yeah, and yeah, please remember that your model also has to be on the GPU for you to train the model. You need to transfer all the tensors as we previously discussed, X, the data pairs, training set, validation set, everything. And you also need to move the model to the device. For models, we have the .train and .eval methods. So before training, we should run the model .train. And this essentially tells the model that you have to save the gradients. And when validating or testing, we run model.eval. What it actually does is it tells the model that it doesn't need to save the gradients, and that saves memory and time. A common mistake is to forget to toggle back to train after. So you'll run one training pass for validation pass, and then you forget to turn it back to train. And in that case, the model is not going to learn anything. So here we have, this is something that we've already gone through, the data set and the data loaders. The sequential class, we've moved the model to device. Here, this is the number of epochs or the number of iterations that we're asking the model to do while training. So for every epoch, we ask the model to train. And for X and Y, that is the question and answer pair in the train loader, which is the data loader for the training data set. We first move X and Y to device. The model is already on the device thanks to this. And then we just find the output by applying the model on the X. Yeah, so now that we've run X through our model, we got the Y cap. And if you remember, we need a teacher to tell us how wrong our Y cap is from the actual answer Y. This is where the loss function comes in. It is also known as a criterion. For most of the classification tasks, you are going to use cross entropy loss. And you can go over the specifics, I think not next, but the next to next lecture. So here what you do is then you define a loss, which is depending on the criterion that you've defined here. We've defined cross entropy loss over here. So you give the criterion the output that your model got and the actual output, that is Y. And obviously our aim is to minimize this loss. That's where back propagation comes in. What Abby was actually going through in her theoretical part, the initial loss that she was specifying, which was the D error, was actually this loss. So back propagation is a process of working backwards from the loss and calculating the gradients of every trainable parameter with respect to the loss. Every trainable parameter here essentially means the weights and the biases. And the gradients will tell us the direction in which we need to move to minimize the loss. Yeah. For now, we'll stick with an intuitive explanation. That is, back propagation is a method of assigning blame. So think about some parameter P in the model. Backprop will give us a number delta P, and this delta P will tell us that the actual value of P that we should have is off by this particular quantity, and that is actually causing the final output to be different from the true answer. Right. Then what we do is we do loss dot backward. So as you guys remember, in the model class, we just had the forward. We said PyTorch takes care of the backward through its computation graph. You just need to call this backward function, and it will backprop all the gradients with respect to the loss. And model.train that we've actually specified here, that allowed us to compute the gradients. If it had been in the evaluation state, you wouldn't have been able to do this backward because it did not save the gradients at all. Yeah. So backprop will only compute the delta P values, that is by how much it thinks that you need to change the weights and biases, but it won't actually update them. Now what we need to do is, using the learning rate and using this delta P value, we actually want to update the value of P. And this is where the optimizer comes in. Learning rate is one of the most important hyperparameters throughout all the homeworks. So depending on your learning rate and how you vary your learning rate, your model will be doing exceedingly well or not that well. So this is a hyperparameter that controls how much we should believe in delta P. So for the first initial iterations, let's say if my divergence is too high or the loss is too high, and the delta P value is too high, if I keep on moving, if I keep on subtracting or adding delta P to the actual P value, it will keep on varying. So the learning rate kind of controls that. So we set learning rate as 0.001 or 10 power minus 3 or so on. And that helps us understand how much we should trust the delta P values in each of the iterations of the model. In an ideal world, obviously delta p is a perfect assignment, but it rarely happens. So that's why we actually use the learning rate to control the value of change that we do for p. If it's in the right direction, again, the delta p will give a similar value in that same direction, and then we update it again. So it's not like we are missing out on any step here. Yeah, so here we've initialized the learning rate with 10 power minus 4. Important, I think someone asked this on the chat as well, which was 0 grad. So every call to backwards saves the gradients for each parameter in the model. However, calling the optimizer.step. So optimizer.step is what will actually change the weights using the learning rate and the delta p value. It does not delete these gradients after using them. So to delete them, we use the 0 grad, which is after every epoch or every batch rather, we actually remove the gradients. So that is what 0 grad is used here for. Yeah, so the general order of these steps are that we run X through the model, we compute the loss, then we call the backward that actually does the back propagation. Then we step the optimizer doing optimizer.step, and then we zero out the gradients. So after this piece of code, this is the training loop. After this, you would do the validation loop. You would perform validation to see how your model performs on data it is not trained on. Because sometimes what happens here is you guys might be aware of this term overfitting, where your model learns the intricacies of your training data so well that it is able to completely fool you based on the training values. So what you do is you try to find the answers that the model will give on a completely unseen data set for the model. And that's how you know how good the model is at, how good your model is performing in real life or how it will perform on an unseen data set. Okay, I think here. So one last thing that I would like to say is that even though you don't realize it, validation set also might be biased, because based on the validation results, you will actually vary your learning rate, or you will vary some hyperparameter of your model, which makes the performance on the validation set also biased after a point in time. So you need to take utmost care while that you don't rely completely on the validation set, or you, after some iterations of your model, you actually run it on the test set, submit it to Kaggle and see how you're performing, so that you're not in for a rude awakening that my validation accuracy is 94, why is my test accuracy just 80? Right. Yeah, the link to the example notebooks that you can use, I think there is one on MNIST dataset, which is the handwritten digits dataset that we've actually trained the models on. So this has all the steps that I described today. So you can just go through this link and go through all of the material on there. I have a lot of questions waiting for me. For the people who don't have questions, it's already 9:53, so you might leave. I'll go through the, so people who have questions, I'll just stay back and answer those. Oh yeah, a couple of memes before you guys leave. This is what happens if you train the entire model on your CPU. You will be in tears. This also sometimes happens when you are on Collab free. Yeah, and this is what CUDA essentially does, is that you try to train something and you get an error from the GPU saying that in terms of RAM, we have no RAM left. There's not much you can do except remove all your dangling tensors, clear the cache, or restart the entire instance. Yeah, yeah, backprop actually came into limelight, or came into the picture a few years after it was actually published in 1986. And yeah, we definitely love it. Yeah, that's all. People who don't have questions can leave. I'll answer the questions. I hope you guys understood how to code. I had to rush through the last part, so I'll try to hold an additional half an hour office hour today. If I do get time, I'll post that note on Piazza so that anyone who has questions is not left unanswered. Okay. So we need to run on dot train every time we come back for training. Yep, this is exactly what you do for every epoch you come back to dot train. How to decide the right number of epochs? Well, number of epochs is kind of a hyperparameter, but if you actually just leave it to be extremely high, right, and you keep on monitoring your loss for training as well as validation and the accuracies, you know that this is a good stopping point, and you have some early stopping mechanisms as well, where if the performance is not increasing, the model just stops training. So yeah, you can choose the number of epochs to be exceptionally high, like 100 or 200, and then stop whenever you feel is right. One important thing, oh my god, half of the people have left, but yeah, one important thing that I missed was that whenever you're training a model, every checkpoint you'll need to save. This will be covered in the boot camps for the homeworks as well. Every checkpoint of the model should be saved on your instance, should be saved on Google Drive, so that even if you terminate your instance, all of that is not lost. Because when you finally see the graph of the loss or the accuracy, you know where the model started overfitting, and you take it just one epoch before that and you choose your best model. Model.train is using forward function of the model class we created. Yes. So our P1s of the homework gonna be implementing this lower level algos like forward pass, back prop, and P2s are gonna be yes. Bharat, that's what P1s are going to be. You're going to be implementing some of the classes like the linear layers, the CNNs, the forward pass for that, the back prop for that as well, because you won't have a computation graph built in that will do the back prop for you automatically. We have a bonus homework for that, but that's too much foreshadowing. And yeah, you'll be implementing all of these algorithms in Numpy from scratch. And in P2s, you can either use the PyTorch versions, or if you're confident on the versions you have written yourself, you can use those as well. Or you can use TensorFlow. It's just that we don't have a lot of support for TensorFlow among the TAs. How do we specify a decaying learning rate in PyTorch? So you have learning rate schedulers. So the learning rate schedulers actually, learning rate schedulers help you to do that. You can have a step LR, you can have a reduce on plateau. So just look up schedulers. Could we move model.train outside of the for loop? No, you cannot. So for every epoch, you need to tell the model that it has to be back on the training loop. Yeah, Sean already answered LR.scheduler. Are we gonna cover how to choose different optimizer and find the appropriate learning rate? Not today, not today. This is just a recitation for helping you guys write your first MLP code. All of the hyperparameter tuning and all of that optimization will be covered in the recitations to come and the lectures to come. And you yourself will have a lot of experience on it while you do the homeworks. For optimizer like Adam, do we still need to use zero grad at the beginning of training? Yes. There aren't really a best way to do it. Okay, Abby has answered. Okay, thank you for your comments, Yukun. Can you explain again the role of optimizers? Sure. So Gopi, what optimizers essentially do is, let me go back. Yeah, so now you have the delta P values after you've done the back prop on your model, right? You have these delta P values or delta W or delta P values for all the weights and biases, but your weights and biases are yet not changed. So doing backward will not actually change those weights. What is going to change those weights is the optimizer, depending on the learning rate that you've given it. So let's say if the delta P value is 10 and your P value was 100. So this 100 minus 10, which gives 90, is not going to be done by the backward. What the optimizer will do is, let's say you specified a learning rate of 0.1. It will do 10 into 0.1, which is 1. And then it will subtract it from the P value, which will give you a new updated P value of 90. Is that clear? Yep, it's the update step. Exactly. Where was I? Yeah. Thanks, Prof. Simran, for your comments. Can you explain what zero grad is for again? Sure. So yeah, what it does is you've collected gradients at this lost or backward stage, right? At this point, it's not going to forget the gradients, and those gradients will be carried forward into your next batch. You don't want to do that, right? Because they are the gradients from your previous batch. So what you do is that you specify zero grad. So it converts all the gradients to zero, and then it will finally compute new gradients for your new batch. Thanks, Eric. Thank you, Nicholas. Thanks for appreciating the memes. Yeah, thank you guys. When will we receive these slides? These are already posted on the deep learning website. How do we customize the loss function? So PyTorch has a variety of loss functions that you can use, but if you actually want to customize the loss function, you can just code it up from scratch. You will be actually doing it in the P1s. You'll be doing the common loss functions. You'll be coding those up in the P1s of the homeworks. That will help you write your own loss functions if you want to customize it. Could explain how to update weights that are immutable. Okay, so the weights, the tensors themselves are immutable, but what PyTorch does is it actually does a computation of it. So it will say P equal to P minus learning rate into delta P. So that the value of that computation will be the new weights. So the tensor is still not immutable. It's another computation done on top of the tensor. So you cannot actually go and say that the first element of the tensor has to be 2.0, right? You can say that if the tensor was 1, the new tensor is the old tensor plus 1. Will it be, sorry, why tensors are immutable? I believe I just covered that. If you have any other doubts, please feel free to ask. Will it be faster given you have enough GPU memory to move the entire data set to No. I don't think it will be that much faster, although I've never tried it because I never had that much GPU memory, to be honest, because the data sets are huge and the GPU RAM, the best I've gotten is 16 gigabytes. It would be helpful to think of tensor as storing computing instructions rather than values. So exactly. So just what Abby said. Could you please explain more on the collect and get item function? What's the difference? Okay. Fan, are you still on the call? Okay, yeah. So where is the data set? Okay. So the get item function, what it will do is when you give it a particular index, it's going to just get you the X and Y, the question and answers for that particular index. Okay, so it's going to be run every time you iterate through the data loader. What the collate function does, it's collate. So what the collate function will do is it will actually group these into batches. So professor is going to go over the theory for this, but it's actually not useful. It's not useful running each and every question and answer pair through the model and trying to train the model on that. Instead, you get the best results when you group them into mini batches. So you divide your entire data set into mini batches. So what the collate function will do is using the get item, when it gives an index, the get item will return the corresponding X and Y. The collate function is just going to group them up into batches. That's all it will do. Is that clear, Fan? Okay, perfect. Where do we save checkpoints if you're using AWS? Terminating the instance will delete everything, right? Should we leave them stop? No. If you're not using an instance, I would suggest, like, if you're not going to be using the data on that instance again, I would suggest just terminating the instance because it will save you the storage cost as well. If you stop it, you are just save the computing cost, but you still incur the storage cost. So I would suggest that you save the checkpoints on your instance for sure, and you download them after the training is done, but simultaneously you push it to Google Drive. So you have the G Drive package in Python that will help you upload to Google Drive. Okay. Yeah, I believe those are all the questions. I'll wait for another minute if anyone has any other questions that they would like to go over, and I'll also announce the extra office hour in some time after I understand my schedule. So please go ahead, ask any questions. Yeah, there are no more questions. Okay, Abby, I think we can stop and you can just save the recording.
Yeah, sure.
Oh, sorry, there's one more question. So collect function is important mainly for batch size allocating data load. It's important for grouping it into batches, and it's the collate function. So I think you would have seen this function in your, I've just put it, I've put it to Abby as. So it's the collate function, and you must have seen this in some of your homework zeros, I think, the collate _fn. So this actually helps group the indices that you get from the get item function, each of the pairs that you get from the get item function into batches. I think that's it. Thank you guys for listening to me speak on a Friday morning, and have fun solving the quiz. Bye.
Bye.